Approaching Mach 1, just hundreds of feet above the Sea of Japan, at this speed, water doesn't look like liquid anymore. It looks like pavement. Viktor Belenko is in a desperate race against time and dwindling fuel as he crosses toward Japan. He isn't just stealing a plane. He's betting his life that the world he was taught to hate is the only one that will keep him alive. The Americans call this aircraft the Foxbat. For 8 years, they've been building billion-dollar defense systems to counter an agile superweapon that can outturn anything in the sky. They're wrong. It's a fuel-chugging sledgehammer, and Belenko is currently swinging it at their front door. The gauge is dropping faster than his altitude. At sea level, the Foxbat drinks fuel like it's bleeding out, 3 times the normal burn rate. The engineers who built this gauge never imagined someone would fly this low, this long, toward a coastline that exists only as a coordinate scratched into his kneeboard. According to biographical accounts, he's already well past the point of no return. If he crashes, the wreckage still tells the story. If he makes it, every defensive calculation the Americans have made for the past decade becomes obsolete before breakfast. Either way, the world's most feared interceptor is about to become the world's most expensive intelligence failure. The coast lies somewhere ahead in the haze. Earlier that day, September 6, 1976, Belenko walked the pre-flight checklist at Chuguyevka Airbase on the Soviet Pacific coast. He signed for a routine training sortie over the Sea of Japan, a mission profile he had practiced numerous times. Ground crew fueled the MiG-25 to standard load, enough for 90 minutes at high altitude with a comfortable reserve. Belenko did not correct them. He knew the numbers would work only if he stayed above 50,000 feet, where the air is thin and the engines sip fuel efficiently. He had no intention of staying high. The mission paperwork showed a scheduled return later that morning. He filed it without hesitation. The MiG-25 Foxbat was built for one purpose: to chase NATO bombers at 80,000 feet before they could reach Soviet cities. 2 massive Tumansky R-15 turbojets provide the thrust, each one a 20-foot-long afterburning monster that burns nearly a ton of fuel per minute at full throttle. At design altitude, cruising at Mach 2.8, the Foxbat is the fastest operational interceptor in the world. The airframe is not titanium, despite Western assumptions. It is stainless steel, heavy and heat-resistant, chosen primarily because Soviet industry struggled to weld and machine titanium on the massive scale required for the airframe. The radar uses vacuum tubes instead of transistors, a deliberate choice to survive the electromagnetic pulse from a nuclear detonation. Belenko knew the fuel math before he ever climbed into the cockpit. Under typical training parameters, the aircraft often carried a reduced fuel load for routine intercept missions, though Belenko's defection flight reportedly began with a nearly full load of approximately 14 tons. His plan required low-altitude flight to avoid Soviet radar, and low altitude tripled the fuel burn rate because the engines must push through dense air at full power just to maintain speed. That left him with zero margin. If he climbed to save fuel, he would appear on every Soviet radar screen between Vladivostok and the Japanese coast. If he stayed low, he would reach Japan with fumes in the tanks or crash into the sea halfway across. Belenko filed a standard coastal patrol route, a lazy racetrack pattern that would keep him within 100 miles of Soviet airspace. Ground controllers expected him to return in 90 minutes. He signed the logbook, accepted the weather brief, and walked to the flight line without drawing attention. The base commander had no reason to suspect anything. Belenko was a senior lieutenant with years of flying experience and a spotless service record. Though relatively new to the MiG-25, having transferred to the unit roughly a year earlier, he had flown intercept missions against American reconnaissance aircraft and knew the protocols by memory. He climbed the ladder, strapped in, and started the engines exactly as he had done 100 times before. What ground control didn't know was that his aircraft carried a full fuel load, unusual for a routine training sortie, but essential for the journey he had planned. Western intelligence believed the MiG-25 was an agile titanium superfighter, a design response to the American XB-70 Valkyrie bomber program. Analysts assumed Soviet engineers had matched or exceeded Western materials science, building a lightweight interceptor capable of high-speed turns and sustained Mach 3 flight. The prevailing assessment within NATO tactical circles was that the Foxbat represented a threat that existing fighters were ill-equipped to challenge, a perception that influenced everything from pilot training to strategic planning. The assumptions were built on satellite photos and defector reports, none of which had provided a close look at the airframe or engines. Belenko knew the truth. The MiG-25 was a 64,000-pound sledgehammer, not a scalpel. Belenko had to fly at 200 feet to stay below Soviet ground radar coverage. The Foxbat's design mission kept it above 50,000 feet, where radar returns from the aircraft's massive steel airframe were expected and tracked as friendly. Down at wavetop level, he became invisible to ground stations, but visible to physics. The engines, designed to breathe thin stratospheric air, now gulped dense sea-level atmosphere. Fuel consumption spiked immediately. Every minute at low altitude cost him 3 times the fuel he would have burned at cruise altitude. The math was unforgiving. He had perhaps 40 minutes of fuel remaining, and Japan was 35 minutes away if everything went perfectly. The engines were screaming. Belenko could feel it through the stick, a vibration that shouldn't be there. The Tamansky R-15s were built for the razor-thin air at 80,000 feet, where every gulp of oxygen comes easy. Down here, at wave height, the engines were choking on thick sea air, gulping fuel like a drowning man gulps water. He kept the throttles at military power, just below the afterburner detent, trading raw speed for every extra minute in the air. But the fuel flow meters told a brutal story. At this rate, the tanks would be bone dry in less than an hour. The engines struggled in the dense, low-altitude air they were never designed to traverse, the afterburner nozzles operating so far outside their designed efficiency range that specific fuel consumption had gone through the roof. No autopilot could save him here. The Foxbat had never been designed to fly this low for this long. He was asking a high-altitude interceptor to become a crop duster, and the machine was bleeding fuel with every second he asked. Belenko had no Japanese navigation charts and no way to obtain them without alerting Soviet intelligence. His only reference was a mental map built from years of studying Western geography in secret. He knew Hakodate was a civilian airport on the northern tip of Hokkaido, approximately 400 miles from his departure point across the Sea of Japan. He had memorized the approximate latitude and longitude, but he had never seen the airfield from the air and had no photographs to confirm runway orientation or length. His plan depended on visual acquisition of the coastline and the hope that the airport would be obvious once he reached land. Belenko could not use his radio to contact Japanese air traffic control without alerting Soviet intercept stations. Every military and civilian frequency in the region was monitored around the clock by signals intelligence units stationed along the coast. A single transmission in Russian or broken English would trigger an immediate scramble of interceptors and a diplomatic incident before he crossed into Japanese airspace. He flew in complete radio silence, relying on the assumption that Japanese radar operators would eventually notice an unidentified aircraft approaching their coast and scramble fighters to intercept. By then, he calculated, it would be too late for the Soviets to stop him. If Belenko overshot Hakodate or misjudged the landfall, his critically low fuel would leave him little margin for error. Historical accounts indicate he had roughly 30 seconds of fuel remaining after touchdown, enough to circle the airport, which he did 3 times, but not enough for extended searching. The MiG-25 he flew was equipped with a KM-1 ejection seat, designed for high-speed performance with some low-altitude capability. At 200 feet over water, an ejection would have been extremely hazardous. The seat's rocket motor would fire him upward, but the parachute would have only seconds to deploy and slow his descent before water impact. A high-risk scenario with significant chance of injury or death. Belenko needed to find an airport quickly. When he spotted Hakodate, he circled it multiple times, reportedly narrowly avoiding a commercial airliner before committing to his final approach and landing. Early in the flight, Belenko reportedly activated his aircraft's emergency distress beacon for 40 seconds, a calculated deception to simulate a crash before going radio silent. Soviet ground controllers would observe the distress signal, followed by the fighter's sudden disappearance from their scopes. According to available records, the duty officer scrambled to confirm whether Belenko's aircraft had crashed near his home base of Chuguyevka. The base would report no emergency, no wreckage. Protocol required an immediate scramble of interceptors, but by the time alert fighters reached altitude and sorted the radar picture, Belenko would be crossing into Japanese airspace. He reduced throttle to minimum sustainable power, trading speed for every last mile of range. The fuel gauge needle touched the red arc. The fuel gauge dropped faster than Belenko's pre-flight calculations predicted. He had estimated burn rate based on sea-level performance data from the technical manual, straight and level flight in calm air, but morning turbulence over the Sea of Japan forced constant throttle corrections. Each spike in fuel flow lasted only seconds, but the cumulative effect drove consumption well beyond his worst-case projection. He adjusted throttle to the absolute minimum, accepting slower cruise speed, trusting the extra minutes of endurance would matter more than the extra minutes in the air. Then a warning light flashed in the cockpit, just once, a brief pulse that made his chest tighten. He stared at the instrument panel, steady now. But in a MiG-25 running this low on fuel, such a warning would typically signal the pumps beginning to draw from the bottom of the tanks, pulling vapor along with liquid. Next time, it wouldn't be a brief flash. Next time would be silence. Both engines flaming out at once, the cockpit going dead quiet, except for the wind. The coastline was still not visible. Through scattered clouds at 11 o'clock, Belenko spotted the dark line of the Japanese coast. He cross-checked the heading indicator, searching desperately for any recognizable landmark. The fuel gauge showed less than 5 minutes remaining, possibly less if the indicator was optimistic. Unable to locate his intended target of Chute Airbase through the cloud cover, he scanned the coastline for any runway and spotted a narrow strip running along the bay at Hakodate, flanked by commercial buildings and a small terminal. According to later accounts, he circled the airport multiple times, bleeding off the MiG's excessive speed while assessing the short civilian runway below. As he maneuvered into position, he reportedly came dangerously close to an All Nippon Airways Boeing 727 that was departing the same runway. A standard landing approach would include at least one orbit of the airfield to confirm wind direction, check for obstacles, and establish a stabilized descent profile. Belenko's fuel was critically low, leaving him with very little margin for maneuvering and no way to communicate his emergency to the tower. He began a steep descent toward the airport, lining up for the runway at a dangerously low altitude, and extended the landing gear. The hydraulic system groaned as the gear doors opened and the main struts locked down. Drag increased immediately, and the airspeed began to bleed off faster than he intended. He added a touch of throttle to arrest the descent rate, knowing every second of power cost him distance he could not afford to lose. Belenko committed to the approach with the runway centerline aligned in the windscreen. Hakodate Tower had not cleared him to land because he had never contacted them. According to historical accounts, a civilian aircraft was departing the runway directly in his path, the crew unaware that a Soviet interceptor was 30 seconds behind on final. Belenko had no idea if the runway was long enough to stop the MiG-25. He knew the aircraft required more than 8,000 feet under normal conditions, and the runway ahead looked far shorter. He also knew that any attempt to abort the landing would leave him with no fuel and no options. The throttles came back to idle. The runway threshold passed beneath the nose. The runway is rushing up. Belenko's MiG-25 needs 8,200 feet to stop from 180 knots. Hakodate's civilian runway? Historical accounts vary, but the usable length for an emergency landing may have been as little as 5,900 feet. If true, he's 2,300 feet short. The physics are brutal. Kinetic energy equals 1/2 mass times velocity squared. His jet weighs 64,000 pounds. Every single knot of excess speed becomes energy the brakes and drag chute must dissipate. Come in at standard approach speed, and he'll rocket off the far end into whatever lies beyond. He has 3 tools to bridge that gap: slower approach speed, maximum braking, and 1 drag chute in the tail cone. That's it. The math doesn't negotiate. The total kinetic energy at touchdown had to be dissipated entirely by the wheel brakes and the drag chute. The MiG-25 had no thrust reversers. The wheel brakes worked by clamping steel friction pads against rotating brake discs on each main landing gear strut. Friction converted kinetic energy into heat, and the heat had to be absorbed by the brake assembly without causing the pads to fade or the tires to fail. Sustained maximum braking generated temperatures exceeding 1,000 degrees Fahrenheit. At those temperatures, brake fluid could boil, rubber tires could catch fire, and the friction coefficient could drop sharply, reducing stopping power just when it was needed most. The drag chute deployed at approximately 160 knots, adding massive drag force, a parachute canopy inflating behind the tail. Between 160 and 80 knots, the chute did most of the work, slowing the aircraft by nearly half its initial speed. Below 80 knots, the airflow couldn't keep the canopy inflated. It would collapse into a useless bundle of fabric, and the wheel brakes would have to carry the entire remaining load. Belenko's margin for error? Almost nothing. Touchdown too fast, and the chute wouldn't have enough runway to do its job before collapsing. Too slow, and he risked a stall or a hard landing that could collapse the gear. Either mistake would end the same way. Every knot of excess approach speed cost approximately 200 feet of additional runway. The relationship was not linear because kinetic energy increased with the square of velocity, but the rule of thumb held true across the approach speed range. Belenko needed to land at minimum controllable airspeed to maximize his stopping margin. For the MiG-25, that speed was roughly 150 knots, well below the recommended approach speed of 180 knots. Flying that slow increased the risk of a stall on final approach or a hard sink rate at touchdown, either of which could collapse the landing gear or cause the aircraft to porpoise down the runway out of control. The choice was between too fast and too slow, with no safe middle ground. The runway rushed up at him. One mistake with the throttles, one miscalculation of his descent, and the landing gear could snap on impact. Historical accounts suggest he was traveling far faster than the standard approach speed, closer to 220 knots, rather than the typical 150, leaving virtually no margin for error. The main gear struts were designed to absorb a descent rate of up to 10 feet per second at normal landing weight, but Belenko had no way to precisely control his sink rate on short final, with the throttles at idle and the aircraft at minimum speed. The struts used hydraulic shock absorbers to cushion the impact, compressing under load and then extending to keep the wheels in contact with the pavement. But if he came in too hard, if the struts bottomed out and compressed fully, the remaining impact energy could transfer directly into the airframe, potentially shearing critical mounting hardware and buckling the undercarriage. The MiG could crumple onto the runway with no way to abort. Belenko brought the MiG-25 onto the runway at what witnesses estimated to be well over 200 knots, considerably faster than the aircraft's standard landing speed because the sink rate was increasing and he had no choice but to plant it. The main gear hit first, compressing the struts halfway. Then the nose gear slammed down. He immediately deployed the drag chute and stomped full brake pressure. The chute blossomed behind the tail, jerking the nose down and adding massive drag force. The runway end was already visible through the canopy, closer than he expected. He kept maximum pressure on the brake pedals. The airspeed indicator unwound rapidly as the chute did its work. Airport workers and bystanders watched in shock as the Soviet fighter hurtled past. Belenko applied the brakes so intensely that they likely reached extreme temperatures during the emergency deceleration. Heat radiated from the brake discs, visible even in daylight. The front tire blew out under the extreme pressure of the emergency landing, vibrating the entire airframe. Belenko felt the judder through the stick and rudder pedals, but held brake pressure constant. He experienced significant deceleration forces as he struggled to stop the heavy interceptor on the short civilian runway, enough to feel the harness straps cutting into his shoulders. The drag chute remained inflated, pulling the tail straight and keeping the nose gear planted. As the aircraft slowed toward taxi speed, the drag chute's effectiveness diminished, and the remaining deceleration load transferred entirely to the brakes. The runway end was now less than 1,500 feet away. At 80 knots, the drag chute collapsed into a tangled ribbon behind the tail. Belenko had 1,200 feet of runway remaining, and the brakes were the only tool left. The left tire was completely destroyed, the wheel rim grinding directly on the pavement and throwing sparks. The right main tire was failing, but still holding air. Brake temperatures peaked at 1,100 degrees Fahrenheit, well into the range where pad material begins to degrade. The airspeed dropped through 60 knots, then 40, then 20. Belenko kept the brakes locked. The MiG-25 rolled to a complete stop 800 feet from the seawall, the engine still running, brake assemblies smoking, and the left wheel rim glowing orange. Belenko shut down the engines and sat motionless in the cockpit for several seconds, hands still gripping the stick and throttles. Ground crew and airport security surrounded the aircraft, unsure whether to approach. He opened the canopy, unstrapped, and climbed out of the cockpit, dropping to the ground using fuselage handholds. His flight suit was soaked with sweat. According to most accounts, his first action was firing 2 warning shots from his service pistol to keep people away from the aircraft. He then surrendered to Japanese authorities, making clear his intention to seek asylum in the United States. Within minutes, Japanese police cordoned off the runway and radioed the incident to Tokyo. The MiG-25, the Soviet Union's most secret interceptor, was now sitting in the open on a civilian airport apron, visible to anyone with a camera. The Soviet Union demanded the immediate return of the aircraft and pilot, claiming Belenko had suffered a navigation error and landed by mistake. Japanese authorities refused, citing Belenko's explicit asylum request. The United States, operating under the Mutual Defense Treaty with Japan, immediately requested access to inspect the MiG-25. The Soviets protested, arguing that any disassembly would violate diplomatic protocols. Negotiations stalled for 3 days while the aircraft sat under guard in a hangar at Hakodate, surrounded by Japanese self-defense force personnel. On September 9th, American intelligence officers arrived with a team of Air Force engineers and a strict deadline: disassemble, document, and reassemble the jet before diplomatic pressure forced its return. The engineers had never seen a MiG-25 up close and had no technical manuals. They worked with hand tools, photography equipment, and an absolute prohibition on leaving any evidence of tampering. Every bolt removed was photographed in place, labeled, and stored in numbered bins. The airframe was primarily stainless steel, far heavier than the titanium construction Western analysts had assumed. The welded seams and riveted panels had to be disassembled in reverse order to avoid damaging the structure. The radar bay presented the biggest challenge. The most sensitive components were sealed inside welded stainless steel housings. Breaking the welds would leave permanent scars that Soviet inspectors would immediately recognize as evidence of espionage. The radar system used vacuum tubes instead of transistors, a design choice that stunned American engineers. Vacuum tubes were considered obsolete in Western avionics, replaced by solid-state electronics in the early 1960s. The reason for their use in the MiG-25 became clear. Vacuum tubes are immune to the electromagnetic pulse generated by a nuclear detonation, which would instantly fry transistor-based circuits. The Soviets had designed the Foxbat to survive and continue operating in a nuclear battlefield environment, where American fighters would be blind and unable to coordinate. Analysis of the radar system revealed an approach that surprised Western intelligence. Rather than sophisticated digital algorithms, the Soviets had opted for overwhelming raw power, using the vacuum tubes to generate signal strength that could burn through standard electronic countermeasures that American forces relied upon. They'd been told it was titanium. Every intelligence briefing, every satellite photo analysis, every defector report: titanium. The Soviets had supposedly cracked mass production of the wonder metal, leaving American metallurgy in the dust. But when the engineers finally pressed their instruments against the MiG-25 skin, the readings came back wrong. Stainless steel alloy, not titanium. Steel. The fuselage, the wing structures, all of it. Titanium was lighter and better suited for sustained high-speed flight, but Soviet metallurgy could not produce it in the quantities required for mass production. So they'd use stainless steel instead. Heavier, yes, which explained the MiG-25's poor maneuverability, but also heat-resistant and far cheaper to manufacture. The metallurgy samples revealed welding techniques that prioritize production speed over weight reduction. The design philosophy snapped into focus. Build an interceptor that could be produced quickly in wartime, even if it sacrificed agility and range. The myth had been shattered by a simple metal test. The disassembly revealed that the MiG-25 was optimized for straight-line speed and high-altitude interception, not dogfighting. Its turning radius at Mach 3 would rip the wings off due to excessive G-loading on the heavy steel airframe. The maximum sustained turn rate was roughly 2.5 G, far below the 6 to 9 G capability of contemporary American fighters like the F-15 Eagle. The myth of Soviet technical superiority, built on 8 years of satellite photos and speculation, collapsed in a hangar in Hakodate. Western air forces revised threat assessments and shifted fighter design priorities. The MiG-25 was not a superweapon. It was a brute force solution to a specific mission: intercept high-altitude bombers before they reached Soviet airspace, regardless of cost or elegance. 67 days. That's how long American and Japanese engineers had to extract every secret from a Mach 3 interceptor before returning it to the Soviets. The disassembly was systematic and thorough. Teams worked around the clock, documenting every component, every system, every design choice. When the analysis was complete, the MiG-25 was packed into approximately 30 containers, a collection of parts rather than a restored aircraft. The MiG-25 was crated and loaded onto a cargo ship bound for the Soviet Union. But the damage was done. American engineers had extracted everything: radar schematics, hydraulic system designs, metallurgy samples, performance data that rewrote the entire threat assessment for Soviet air defense capabilities. The intelligence windfall remained classified for decades. The cost to the Soviets? Incalculable. When their inspectors arrived to receive the aircraft, they found clear evidence of the extensive analysis and identified roughly 20 missing components. They knew exactly what had happened, and there was nothing they could do about it. Viktor Belenko was granted asylum in the United States and eventually settled in the Midwest, far from the intelligence agencies that debriefed him for months. He provided detailed operational knowledge of Soviet intercept tactics, training procedures, and the day-to-day realities of life as a Soviet fighter pilot. His testimony corroborated the technical findings from the disassembly and filled in gaps that hardware alone could not reveal. He later worked as a consultant on Soviet aviation for defense contractors and wrote a memoir detailing his defection. The Soviet Air Force declared him a traitor and scrubbed his service records. His family in the USSR faced years of scrutiny and suspicion. Belenko would not return to live in his homeland, though he reportedly made a brief business trip to Moscow in 1995 after the fall of the Soviet Union. September 6, 1976 changed everything. One pilot's desperate gamble didn't just expose a plane, it rewrote the rules of the Cold War arms race. Western fighter programs pivoted overnight. Designs built to counter a Phantom superfighter were suddenly reassessed, their missions redefined. The focus shifted to beyond visual range engagement and electronic warfare. The F-15 Eagle, already rolling off production lines, was suddenly validated as more than adequate for any engagement with the MiG-25. Intelligence agencies tore up their threat assessments. Soviet engineering, they now understood, prioritized mass production and nuclear survivability over technical elegance. The sledgehammer, not the scalpel. The MiG-25 flew on for 3 more decades with Soviet and export forces, but the mystique? Gone forever. Viktor Belenko lived in exile, never reuniting with the family he left behind. He reportedly returned to Russia once, briefly, in the mid-1990s, but the Soviet homeland he'd fled was already gone. The price of truth. Isolation. A life rebuilt from nothing in a foreign land. And the lesson? Assumptions built on incomplete data can drive billions in defense spending toward the wrong threat. One defector, with the courage to risk everything, proved what 1,000 spy satellites couldn't.